Hello guys, in today's video we are going to solve LeetCode question number 342, power of 4. It is an even problem. Given an integer n, return true if it is a power of 4, otherwise return false. An integer n is a power of 4 if there exists an integer x such that n is equal to 4 raised to the x. So basically in this question we have to find whether a number is a power of 4 or not. So let us begin with an example which will help you understand the approach for this solution. Given input n is equal to 16, we need to check that if 16 is a power of 4 or not. So we need to consider the number 16. So while we look at number 16, we know that 4's square is 16. So of course it is going to be a power of 4. But there's one property that is being followed by all the powers of 4's. If a number is a power of 4, it means that it will be divisible by 4. So if we mod that number by 4, it will always return 0, or it will always result in value as 0. If we keep on modding and keep on dividing the value, which is a power of 4, by 4, it will return or result in the value of 1 at last. So what we are going to do is we are going to keep a number modding and dividing by 4 until it is not being modded as 0 or not being returning as 0, and we check if the number after being modded resulting in 1 or not. So I'll give you an example so we will better understand with an example. So 16 is a number. So 16, if we mod this number by 4, if we mod this number by 4, it will return as 0. Okay, so we are currently on the right path. But after we know that if it is being mod by 4, it will result as 0. Now we will divide the same number by 4. So we'll 16 mod 4 or divided by 4 will return as 4. Now we'll again check by modding it by 4. So if we mod 4 again by 4, will it return 0? Yes, because uh, 4 is a power, or 4 is a power of 4. Now again we'll divide 4 by 4. It will return a value as 1. Now if we mod 1 mod 4, then it will return value as 1. So we'll stop here because the result of the mod operation is not 0 any longer, so we cannot go for any further. Now we need to check if we reach the value of 1, it means that the number n, which is 16, is a power of 4, because we are able to continuously divide it until we reach the value 1. So if any number follows this property, that if we keep on modding it by 4 and it returns or results in 0, and if we keep on dividing it until we reaches it number 1, it means that it is a power of 4. So let us take another example over here, so we will get a better idea. So we'll take this time number 5. So let us take n is equal to 5. So we need to keep on checking whether the number is divisible by 4. So if the number is divisible by 4, we'll keep on dividing it by 4. Once the number is not divisible by 4, we need to check whether the resulting number is equal to 1 or not. If the resulting number is equal to 1, it means that it is a power of 4. If it has any another number or greater number, we'll consider that it is not a power of 4. So to understand it, first we need to keep on checking whether the n, given n, is a divisible by 4 or not. So if we take 5 and 5 mod 4, so this will return the value as 1 or result the value as 1. So we'll break out of the we'll not go further, because as it is not divisible by 4, divisible by 4, and the mod value is not returning as 0. So we'll check again. So as it is not modded by 4 or divisible by 4, so we are not going to divide it again by 4. So we'll check if is 5 equal to 1. No, it means that 5 is not a power of 4. So we are going to implement this basic approach to check whether the given integer n is a power of 4 or not. Now guys, let us start with the implementation of our logic. So in this function we have to return whether the given integer n is a power of 4 or not. So we know that if a number n is less than equal to 0, then it is not going to be a power of 4. So we'll check initially only. If the n is less than equal to 0, then we'll return false here and here itself. Now we'll use the while loop to check the divisibility condition. So if n mod 4 is equal to 0, it means that n is divisible by 4. So if n is divisible by 4, we'll divide n by 4. Okay, so we'll keep on dividing n by 4 until it is divisible by 4. Once it stops being divisible by 4, we'll check if n has reached the value of 1. If n has reached the value of 1, it means that it is divisible by 4 or it is a power of 4. So we'll return true over here, else we'll return false. So we'll check this code with the test cases. Yes, it is passing the initial test cases. Now let us submit. Yes, it is solving all the test cases. Now let us calculate the time and space complexity of our solution. So space complexity, as we are not using any kind of extra space, it will be O of n, as it is a constant space solution. Now time complexity, so only the while loop is contributing towards the time complexity. Each and every time we are dividing the number n by 4. So it will be a logarithmic solution or logarithmic time complexity, as we are dividing the number every time by 4. So even if the number is large, for example if it is 16, let us take 16 as an example. So if we divide it by once 4, then it will be 4, and then if we again divide it by 4, it will become 1. So it is a logarithmic solution. So each time we are dividing it by 4, so it will be O of log to the base 4 and n, because each time we are dividing it by 4. This is similar to like binary search problem. In binary search, we are reducing the search space by halving the search space or dividing it into 2. So we are either go searching in the first half or in the second half. Similarly, in this case, we are dividing it into 4 and again dividing it by 4 subsequently. So it will run less number of times. So it will be log base to the 4 log n to the base 4 as the time complexity. Now let us try to find an optimal solution for the given problem. So in order to find the optimal solution of this problem, we need to look properly. So for input 16, so let us represent 16 in the binary format. So we'll try to represent 16 in 8-bit binary format. So it will come as 0 0 0 0, 1, 0, 0, 0. So we know that 16 is a power of 4. So and it is having a binary representation as this. Let us take 4. Now let us try to represent 4 in binary format. We'll take 4-bit format only, or let us take 8-bit representation of 4. So it will be 0, 0, 0, 0, 0, 0, 1, 0, 0. Okay. Do you find any similarity between these two? 4 is also power of 4, 16 is also power of 4. Take any other power of 4, convert them into binary format, and we'll find one similarity between them. There's one similarity between them, that all powers of 4 have exactly one bit set in them. In this representation, we can see that only one bit is set to as 1. Similarly, in this uh, representation of n is equal to 16, only one bit is set. Okay, so if a number is power of 2, it will also have only one bit set. Yeah, correct. If a number which is a power of 2, which will also have only one and exactly one bit set. But another similarity that we need to find over here, that is not there in the power of 2. If we check the position, like bit position, so let us consider this 0, 1, 2, 3, 4, 5, 6, 7. Okay, similarly we have 1, 2, 3, 4, 5, 6. Okay, there's a mistake. 3, 4, 5, 6, and 7. Okay, so we have given each bit as a position or position value. We can see that both the ones that are set, they are set in even bit position. Here it is set at position number 2, which is an even bit position, and similarly over here the number bit 1 is set, it is at the position number 4. So we are going to use these two properties to check whether the number is a power of 4 or not. So how are we going to check that whether it exactly has 1 and the set bit is at an even bit position? So for us to check if the number binary representation of any number, it is exactly having 1 in one bit set, what we are going to do is, for example, if we are going to have 16, we are going to take 16 and we are going to perform a bitwise AND operation with 16 minus 1, which will be 15. So why exactly 15? So when, if let us again take the binary representation of 16 over here, and if I write the binary representation of 15 over here, it is going to be 1, 1, 1, 1. So if we minus exactly 1 from the number, any number, so all the bits who are set from the last bit set will be flipping. So this is the last bit which is uh, set, every other bit from here will be flipped. We can see this pattern. So 1 is 0, 0 is 1, 0 is 1, 0 is 1, 0 is 1. And if we perform bitwise AND, so if in the AND table, if it is 0 and 0, it will give the value as 0. If it is 1, 0, it will give the value as 0. If it is 0 and 1, it will still return the value as 0. Draw this table. If it is 1 and 1, it will only return a result in 1. So if we AND number n with n minus 1, it will flip all bits from the last set bits towards right side. And if we AND them, it is not going to result in any value, it is going to be 0. So if and only if there is exactly one bit set in the binary representation of a number, then ANDing it with its n minus 1 will return as 0. So as 16 is having exactly one bit set, ANDing it with 15 will result it as 0. So yeah, we'll use this logic for checking whether a number is having exactly one bit or not. Now next condition or next criteria that needs to be fulfilled to check whether a number is a power of 4 or not. So we are going to use the concept of magic numbers. So basically we know that if a number is a power of 4, then it will have bit set at even position. Okay, so what we are going to do is we are going to add it with a or and we are going to perform a bitwise AND operation with a number which is having bits set at odd position. So even if we AND it, it will result as 0. For example, 16. Okay, so this is the binary representation. This is the binary representation of 16, and we know this is the even position. This is 0, 1, 2, 3, 4, 5, 6, 7. And if we AND this number with a number which is having bits set only at the odd position, it means that ANDing it by a number which is having only bits set at AND number will result in 0. For example, let us consider this number. So this is the even number, so it will become 0. This is odd bit position, it will be uh, 1. This is again even, so it will be set as to 0. This is uh, odd, so we'll put that as 1. This is even, so we'll set it as to 0. This is odd, so we'll put that as 1. It is even, so we'll put it that as 0, and this is odd, so we'll put here as 1. So if we add these two numbers, then it will result as 0. Because 16, the number which is a power of 4, will always have exactly one bit set at even bit position, and ANDing it with a number who's only having bits set at an odd position will return or result the value as 0, 0, 0. If the value here is not 0, it means that it is not a power of 4. That's it. We need to check only these two conditions to verify whether a number n is a power of 4 or not. So now let us start with the implementation of our optimal approach. So we are going to just perform a simple if else conditions, or simple we are just going to check few conditions and return the result. So we can directly do that by using uh, putting the conditions in the return value or return statement itself. So we need to check that n should be greater than 0, because if it is less than or equal to 0, then it is not. And n, if we need to perform bitwise and with n minus 1 should be equal to 0. So yeah, this we are using this part of the code to check that it is exactly having one bit set. And the next part of code, or the next condition, we need to check that whether this bit which is set, it is at an even position. So in order to do that, we are going to AND it with a number which is having bit sets at all odd positions. So what we are going to do is n and 0 x a. Yeah, so 8 times a. Okay, yeah, so this number is basically largest number having bits set at odd position. So we are going to AND it with the n, and if it is equal to 0, then it means that the number is a power of 4. So let us check. Yes, we can see it is passing all the initial test cases. Now let us submit this. Yes, it is working. Now in space, it is again not using any kind of uh, extra space, so it is going to have big O of 1, which is constant space. Again, the time complexity will also be big O of 1, because we are not using any kind of loops or recursions over here. So this will also be one of the O of 1 solutions for this problem. This is one of the nice problems, and I don't think so we can optimize it further. And this solution is suggested because in the description they have given up a follow-up question. Could you solve it without loops and recursion? So this is the solution which is without any loops or recursion, and with this is the solution with O of 1 time complexity. So thank you guys.